When we talk about tangents, normals, and stationary points, we're going to be bringing together ideas from differentiation and then parallel and perpendicular straight lines. So if you haven't watched those videos already or aren't familiar with those topics, I would suggest going over those first. Of course, we are going to be talking about the concepts anyway, just contextually, but for more thorough breakdown, I'd check out those. In general, though, when we mention these terms, we're going to be looking at either lines or points related to a curve. For a tangent, this is a straight line that is parallel to the curve at a point, whereas the normal is perpendicular. So a straight line that is parallel to a curve. Yeah, and the normal is perpendicular. So i.e. the tangent is going to match the gradient of the curve at that given point, whereas the normal is going to be making a right angle to it. So when we're talking about the gradient, this we can get from doing the differentiation of the equation of the curve. We'll get an expression for its gradient at any given point. Of course, it's not going to be a fixed value because with a curve, the gradient changes all the time. So you then plug in the x-coordinate of the point you're referring to, get that gradient. For the tangent, you'll just then use that gradient in your y equals mx plus c. Meanwhile, for the normal, we'll be then referring back to that idea that for normal, so the gradient of the tangent times the gradient of the normal equals -1, or in other words, the gradient of the normal is the negative reciprocal of that of the tangent. Now then, as for stationary points, also referred to as turning points, the idea we'll be working with is that at those points, the gradient, the dy over dx, equals 0. Now we can have three types of turning point. This may be referred to as their nature. You may have a maximum point here. So it's not necessarily the highest point on the curve. It may then keep on going up infinitely. But here, as a local maximum within that specific region, that is like the crest after which it starts coming down again. Alternatively, just the opposite, you have a minimum, which again may not be the lowest point on the curve full stop, but locally it is kind of the trough where it then goes up on the other side. Or you could have it where it levels off, but then carries on in the direction it was going in before. This is referred to as a point of inflection. In any of these cases, because in that instantaneous moment the line is flat, it has a gradient of 0, that's how we can identify where the stationary point is, that turning point. But as to then just, even if we didn't have it graphically shown to us, if we didn't know the shape of the graph, we just knew that this was the coordinate of some turning point. How do you work out mathematically whether it's a maximum minimum point of inflection? Well, for this, you would then take the second derivative. You would differentiate again, and from this, if the answer was greater than 0 when you plugged in the x-coordinate of the turning point, that means that it's a minimum. If it equals 0, then it's a point of inflection, and if it's less than 0, it's a maximum. Now, with the minimum and maximum, this may feel a little bit counterintuitive, because why would a maximum be when your derivative is a negative number, or minimum when it's a positive number? Well, that's because just as how the main differential, the main derivative, is showing you how much the line is going up as it goes across, the second derivative is showing you how is the gradient changing. Well, at the maximum, even though it's starting off with a positive gradient, it's becoming more negative. Therefore, at the maximum, the gradient is a negative change. Whereas at the minimum, even though we're starting negative, we're becoming more positive, so the change in the gradient is greater than 0. And again, in the point of inflection, there's no overall change because it just carries on in the same direction it was in before. So, with those ideas in mind, we can turn our attentions to an example. So let's say we had this cubic graph here, so y equals x cubed minus 2x squared minus 11x plus 12, as we could just see sketched onto our axes here. If first of all we wish to find the stationary points, let's say so it's a stationary point, we know that dy over dx is going to equal 0. We need to differentiate therefore, and then finding out what x value would make that differential equal 0, what would make that true, we can then plug that back into the original to get the corresponding y values. If we just remember to differentiate to get this dy over dx, what we're going to be doing is for each individual term, take the coefficient times the power and then drop the power by 1. So 1 times 3 is just going to be 3, and then that cube is going to drop to a square. Then here, 2 times 2 is going to be 4, that's going to drop to a single x. This is going to just become a minus 11 on its own, and the 12 is going to disappear. So this, we will now say, is going to equal 0. As it's a quadratic, you would usually try to factorise. In this case, it doesn't work out nicely as 2 brackets, so you would have to use a quadratic formula instead, where your a is 3, your b is your minus 4, and your c is the minus 11. From this, if we were to say 3 significant figures, you would get that x is approximately either 2.69 or minus 1.36. Using these, we can then say plug those back into the original to get your corresponding y values. We say y is therefore equal either minus 12.6 or 20.7. If here we wish to just verify the nature of these turning points, let's say we hadn't had the graph to refer to, because looking at this we can see that this turning point here, that's going to be the 2.69 and the minus 12.6, whereas this one is going to, in the x direction, be the minus 1.36, then the y be the 20.7. But let's say we didn't know that, we wanted to verify, you'll take that second derivative, so in this case again doing the exact same steps, this is going to become 6x, that's going to become minus 4, and that's going to disappear completely. Now if we wish to first of all check with the 2.69 and minus 4, we don't even need to work out what that value is. That's very clearly greater than 0. Therefore, that is going to be your minimum. And yes, that just confirms what we said before for the 2.69. That's your minimum. And if we did it with the other one, so 6 times the minus 1.36 minus 4, don't even have to, I mean, you could if you want to, but you don't even have to work that out. In this case, it's very clearly less than 0. Therefore, that is confirmed to be our maximum. So, now that we have that, let's instead move on to the other concept, which was tangents and normals. So if we were to find the tangent to the y-axis, now if we're going to be working out tangent to the y-axis, we're going to need to know the gradient of the curve at the point where it cuts the y-axis. Well, we already know that the differential expression is going to be this, so it's dy over dx equals, and if it's cutting the y-axis, then we know that x has to be 0. So this is going to be 3 times 0 squared minus 4 times 0 minus 11. Well, that's just going to equal the minus 11. Now that we know that this is the gradient of the curve at that point, that's also going to be the gradient of the tangent. So we can just plug that into a y equals mx plus c. The y we can say is going to be 12 by referring back to the very original equation. If you've plugged in that x is going to be 0, that leaves you with y is 12. So 12 equals the minus 11 times by our x of 0 plus c that we don't know yet. But in order to now balance this, we'll be left with saying that c must be 12 therefore. Therefore, your overall equation of the tangent will be y equals minus 11x plus 12. Now, as for the normal instead at x equals 4, again, we're going to start off by referring to the equation of our derivative. So that's now going to be 3 lots of the 4 squared minus 4 lots of 4 minus 11. This gets you a gradient of the tangent of 21. Therefore, your gradient for the normal is going to be minus 1 over 21, the negative reciprocal, because 21 times minus 1 over 21 equals the minus 1. Therefore, again, plugging this into a y equals mx plus c, if you were to put in x is 4, you would find that your y is 0. So it's actually this point here where we're cutting the x-axis. So 0 equals minus 1 over 21 lots of 4 plus c, Therefore, c is going to equal 4 over 21. Now, we could then just put this together and say that's okay, going to be y equals minus 1 over 21x plus 4 over 21. But in these kind of questions, they don't tend to like having fractions here. They want you to have it all in terms of integers. So what we could do is times everything up by 21, so leave us with 21y, then minus x plus 4. And if we just bring everything onto the left-hand side, what that would give you instead is x plus 21y minus 4 equals 0, which is what they may be after if they specify, okay, put it in the form of ax plus by plus c equals 0. Now lastly, even though points of intersection is something that's really going to be covered in its own video, just to mention it here, if the question had then asked you, well, there is a point where the tangent at the y-axis and the normal at x equals 4 intersect, work out what that is. Well, if they're intersecting, then we're saying the same x and y values work for both equations. Therefore, you can substitute one of them into the other. You can replace this y here with the entire expression of the tangent. So, x plus 21 lots of the minus 11x plus 12 minus 4 equals 0. Well, this is going to give us minus 230x plus 248. So just add the add the 230x onto the other side. So 230x equals 248. Therefore, x is going to equal, let's say 3 sig fig, 1.08. And from that, again, just plug it back into the into either of these equations here from either the tangent or the normal, and you're going to get... So we have here that the curve C has the equation of y equals 4x plus 3x to the power of 3 over 2 minus 2x squared. And you first of all, just to find that differentiation there. 0.14. Okay, so that's how we've got to the point of intersection of our tangent and our normal. That's how we've worked out our tangent and normal in the first place. And that's how we've worked out our stationary points. If we're happy with each of those concepts and we'll see how we're kind of bringing together differentiation and the kind of ideas of parallel and perpendicular lines, let's just see how you could get along with an example of your own. Then, once you have that, show that, I'm actually probably going to better label this P, so that point P, which has coordinates 4, 8, is on C, and so finds the normal at that point, at P. And then finally, we're told that this normal cuts the x-axis at Q, and therefore finds the length PQ, so between these coordinates here and wherever it is cutting the x-axis. Consider what concepts we've just been talking about, pause the video, have a go for yourself, and then press play again when you're ready to compare. So, if to start off with, we're just doing our regular differentiation, right? So we're taking the coefficient and timesing it by the power, and then reducing the power by 1, we'll have that our dy over dx, in the first case, that 4x is just going to become 4. Now 3 times 3 over 2, we can either say is 9 over 2 to keep it constant with the fractions, or if you want, you could give a decimal of 4.5. And either way, that will then drop to x to the power of a half. And then here, the 2 times the 2 will be 4, and that will just become a singular x here. Then, to show that that point is on the curve, we're going to have to return to the original equation, as that's what has both the x and the y coordinate. If we sub in this x coordinate here, so you end up with 4 lots of 4, then plus 3 lots of the 4 to the power of 3 over 2, and then minus 2 lots of the 4 squared. Put that in your calculator, you'll find that that equals 8. Well, that's the y coordinate we were supposed to get, so for this x, we do get that y, therefore that point is on the curve. And then as for the normal, because that's the perpendicular straight line going through that point P, we're going to be making a y equals mx plus c. We already have the x and y, but we're going to need the m before we can work out c. So if we work out the gradient of the tangent first, so that our dy of dx would equal 4 plus 9 over 2 lots of 4 to the power of a half minus 4 lots of 4 per the differential we got before. that's going to get us a gradient of the tangent of minus 3. Therefore, the gradient of the normal is going to equal a third. So minus 1 over that gradient, or minus 1 over minus 3, the minus cancel, leaving us with just a positive. Now we have enough information to go about our y equals mx plus c. So the y is 8, so that equals the m of a third times by the x, that's 4, plus c. So this becomes 8 equals 4 thirds plus c, minus that over, you end up with c equals 20 over 3. Therefore, your general equation would be y equals a third x plus 20 over 3. Or if you wanted to turn it all into integers, you could times up by a common factor of 3, making it 3y on the left-hand side, and that equals x plus 20. Now, with this great equation of the normal, we can now find out where that normal cuts the x-axis. So if you're cutting the x-axis, you have no height, your y is 0. So just substitute y 0 in here. So 3 lots of 0 equals x plus 20. Well, 3 times 0 is just going to be 0. So if we just minus the 20 over, we're left with x equals minus 20. Therefore, your coordinates of q are just going to be minus 20 and 0. Now, as for finding the length here, this is where we essentially do our Pythagoras. So we'll have the square root of the difference in the x's. So in this case, that could be the 4 minus the minus 20, because it's minusing the x values, but this is also negative itself, squared, plus the 8 minus 0 squared. So it's all square rooted. And if we do that, put that in the calculator, let's just keep it as a surd form. Let's just say it's going to be 8 over 10. Okay? Cool. So that's just how, again, we've used our ideas of how to construct these tangents and normals, and also just using just more graph-based knowledge of what happens when you cut the axes and so forth to find out each of these pieces of information. With that in mind, let's now just turn our attentions to one further question. So the curve C has the equation of y equals kx cubed minus x squared plus x minus 5, where k is a constant. And first of all, we're to find dy over dx. Okay, well, we'll treat this exactly the same as we usually would. It just so happens that the first term here is going to contain an unknown. So the dy over dx, that's going to get us, so coefficient times power, which is going to be 3k, x, and then the power of 3 drops to power 2. Then here the minus x squared will become minus 2x, and the plus x will just become a 1, because 1 times the power of 1 is 1, and x disappears, as does completely that minus 5. Well, now that we have that, the point A with x coordinate of minus a half lies on C. The tangent to C at A is parallel to the line with equation 2y minus 7x plus 1 equals 0. From this, we are to find the value of k. Well, because we're looking at being parallel, and this here is going to be a straight line, there's no squares or any higher powers in them, in order to get the gradient of this line, to say that the gradient of the tangent is the same as it, because they're parallel, we're going to need to rearrange this so that y is on its own, so that it is in a form of y equals mx plus c. So we'd say that 2y would equal 7x minus 1 by moving these two terms onto the right-hand side. And then, again, the y has to be on its own to fully read off the m and the c. So then you might have 7 over 2, or 3.5 if you prefer, x minus a half. Now, as I say, the gradient here, we're just going to read off as the m value, that being the 7 over 2. So, when we now compare the gradients here to say that they're parallel, all we're doing is making the 3kx squared minus 2x plus 1, that's just equal to that 7 over 2, not the whole thing, right? Just equal to the gradient. Well, from this, if we're going to try to solve, what we could do is we could times up by this 2 to make everything integers. So over here, that's now going to become 6kx squared minus 4x plus 2 equals 7. And you'd now just minus that 7 over. So 6kx squared minus 4x minus 5 equals 0. At this stage, though, we still have two unknowns, and that is why the question has given us what the x-coordinate is, right? We can only solve it as one unknown, so they have to give us something to eliminate one of them. So what we can say is that it's 6k, but now it's minus a half squared, minus 4 lots of minus a half here, minus 5 equals 0. So now just to expand that out and simplify, you'd end up with 6 over 4k plus 2 minus 5 equals 0, or in other words, obviously that's going to become 3 over 2k minus 3 equals 0. So 3 over 2k equals 3, therefore k is going to equal 2. Now that we know that k is 2, we can finally move on to this last bit here, where we'll work out the y-coordinate of A. Because we're after the y-coordinate, we need to return to the very original equation, because that's what equals y. Now I say we know that k is 2, so we're saying that this is y is going to equal 2 lots of, and the x-coordinate is still minus a half, so minus a half cubed minus a half squared plus minus a half minus 5. If you just put that all into your calculator, you end up with a y-coordinate for A of minus 6. Now the question itself does end there, but I just want to look into, once again, the idea of stationary points. And at first, look into why this question didn't ask for a stationary point. Here, if we were trying to solve for the stationary point, if we were to take this expression for the gradient for the differential and just move that over here, if we were to try to now set this equal to 0, because at the stationary point, at the turning point, gradient is 0, knowing that k is 2, we can now say that that's 6x squared minus 2x plus 1. Okay, we're going to set that equal to 0. The problem comes is, first of all, you can't find a way to put that into two brackets. Well, usually that's not going to be so much of a problem because you then just put it in the quadratic formula. But if you do that, then it just gives you a math error. This equation does not have a solution. There is no point where the gradient is 0. This cubic never has any stationary points. That is why they haven't bothered asking you about it in this question. But this here wouldn't work. However, if instead they had made this a minus x from the beginning, that would make this a minus 1 here, a minus 1 here. So we would now have 6x squared minus 2x minus 1 equals 0. This has stationary points. If this is what it had been from the beginning, then they could ask, and if you put that into the calculator, then you would find that x is going to be approximately 0.61 or minus 0.27. And just again plug those back into now the adapted original equation. You would end up with y equaling either minus 5.53 or minus 4.84. Because the reason, other than just, practically it doesn't have a stationary point, but the reason why the previous one didn't work is if you were to plot this quadratic here, where you're looking for the gradients to equal 0, that would be where that line crosses the x-axis. And yet, because it ended in a plus 1, the y-intercept was above the x-axis. The turning point was somewhere up here. It never cuts this line, therefore it doesn't. But once it becomes a minus 1, then instead it does cut somewhere down here. Therefore, we must have these 2 points where it goes through. So again, they don't have to ask you about stationary points regardless if they're possible, but if it's not possible, they're definitely not going to ask. Yet with just a little tweak, you could potentially make it that way. Not that it's the focus of the question, but just showing that you can if you wish to continue practicing it further.